textbook, I like it in general, but this chapter's just like a hodgepodge. I personally would have put the organic compound stuff up earlier with the nomenclature, but here it is. Organic compounds. Early chemists divided compounds into two groups. They called them organic and inorganic. Organic meaning things that came from living organisms. Inorganic came from parts of the environment that were not alive, like rocks and water and stuff like that. And what they found was that those organic compounds decompose more easily than the inorganic ones, and that they could synthesize inorganic compounds, but they couldn't figure out how to make the organic compounds. And so at that point they said, well, only living organisms can make these. And so that was the original division. Now, today, we can make organic compounds in the lab, and we do it all the time. So we define an organic compound a little bit differently. It's not necessarily that it came from a living organism, but really the key to organic is carbon. Organic compounds contain carbon. They mostly contain carbon, hydrogen, and then oxygen, nitrogen, phosphorus, and sulfur are pretty common, but not necessary for it to be an organic compound. And there are sometimes trace amounts of other elements. It's really important to understand that in chemistry we use the word organic very differently than it's used at the grocery store, right? Because you go to the grocery store and here's the organic apples, and these don't say organic. Does that mean they're inorganic compounds? No. In the grocery store, organic means that you didn't use pesticides and herbicides and other chemicals from non-natural sources to grow those plants. They do use chemicals to grow organic fruit and vegetables. Okay? Organic fruits and vegetables are chemicals. Everything is a chemical, right? Just cracks me up. You can buy a bottle of chemical-free sunscreen. What's in that bottle? A vacuum? Because even air is a chemical. So chemists have these little weird mind games they play with themselves. So organic means that it's a compound containing mostly carbon and hydrogen. Here's an example. Methane is natural gas. It contains carbon and hydrogen. This is an organic compound. And so do not get the connotation that organic things are safe. Actually, many organic chemicals are extremely toxic and dangerous, oftentimes flammable, do all kinds of crazy things. So organic does not mean safe. So carbon is the really important thing. Carbon is unique among the elements. This book I'm listening to, A Brief History of Nearly Everything, the guy says carbon is promiscuous. Carbon tends to form 4 bonds, and it bonds very nicely with itself. And so we can get these long chains of carbon atoms. They can also branch and form all kinds of complicated structures. It's like the ultimate building toy, right? It's just, you can combine it with all kinds of things. So the chemistry of carbon is very unique and complex, and that gives rise to all this amazing array of different compounds that can be formed. So it can bond with itself or with other elements. Important to remember, it forms 4 bonds. And to help you remember that, it's in group 4A. It can form single bonds, double bonds, and triple bonds with itself and with other elements, as long as it adds up to 4. So here's a couple examples, well, 6 examples actually. So here we see a molecule that just has carbon-hydrogen single bonds. Here the carbons are in a straight line. They're a chain. This is a branched chain. So here we have 3 carbons, but this carbon is bonded to another carbon, and so it branches, and so they can get very spidery that way. They can also form cyclic structures. So here we have a line of carbon atoms bonded to each other, and one end grabs the other end and forms a circle. Those are cyclic compounds. Here's an example of a carbon-carbon double bond. You see when we have this double bond here, that's 2 bonds, and then carbon will make 1, 2 other bonds for a total of 4 bonds. Carbon's very consistent in that. Here we've got a triple bond, so that's 3 bonds for each carbon, and 1 with the hydrogen, so each of these carbons has 4 bonds. Here we have an example where carbon is forming a double bond with oxygen. Again, each of these carbons has 4 bonds. More flowcharts. So we take all compounds, we can divide these into inorganic, which is what we were talking about with the ionic compounds and the acids and the binary molecular compounds. And then we have this group of organics. And organic compounds can be divided into more categories. And this is just the tip of the iceberg for organic chemistry. Most colleges, there's a 2-semester sequence of organic chemistry, and that doesn't even cover all of it. But we can break these into hydrocarbons and functionalized hydrocarbons. Hydrocarbon, as the name suggests, contain carbon and hydrogen. Hydro for hydrogen, carbon for carbon. They just have carbon and hydrogen. And these are very commonly used as fuels. We find these in oil, in gasoline, liquid propane, natural gas. All of these are examples of hydrocarbons. They're flammable, which can be a good thing. So we're going to learn how to name hydrocarbons. Nice thing about organic chemistry is the rules just seem to be a little more consistent. So we have hydrocarbons that only have single bonds. These are called alkanes. If you have even 1 double bond in that hydrocarbon, then the ending here is changed to -ene, and these are alkenes. If you have 1 or more triple bonds, it's an alkyne. So the hydrocarbon names consist of a base name that's related to the number of carbon atoms and a suffix that is determined by the presence of multiple bonds. So the suffix would be ane, ene, or ein. So this is the summary here. Starting at the bottom here, dec is a prefix meaning 10. You may recognize these prefixes here. So decane is a hydrocarbon containing 10 carbons and all single bonds. Here's hex. If we have hexene, hexene means there's at least 1 double bond. Now, what's a little different is the first 4. Right? Look at those guys. Methyl, methane, ethane, propane, butane. Nice, right? Well, at least organic chemists use those same prefixes a lot. How do you remember those guys? Mom eats pickled bananas. Maybe she's pregnant. Oh. And I learned this, probably in college. And to this day, when I am concerned that I'm getting my name right, I will mutter this in my head. Mom eats pickled bananas. Oh, it's butane. Because otherwise they just do not make sense. But so mom is for meth, eth, prop, and but. And then you put an ending on the end. So propyne, Propyne, would have how many carbons? 3. 3 carbons, and it would have at least 1 triple bond, right? These are some common hydrocarbons. So here's methane, meth meaning 1 carbon. Propane, prop means 3. Butane has 4. Pentane has 5. Here's ethene. Ethene has 2 carbons with a double bond. And here's ethyne, 2 carbons with a triple bond. And here this gives you a space-filling model and where you might find these compounds. These organic hydrocarbons are in use all around us. And we just, don't even think about it. Functionalized hydrocarbons have something different about them. So they're going to be, we call it a functional group because this difference that a functionalized hydrocarbon has affects the function of the molecule. It's going to react in a different way. Even a carbon-carbon double or triple bond can be called a functional group. And we can group these functionalized hydrocarbons based on what their functional group looks like, and I call them families. So here we have methanol and isopropanol. Both of these have the functional group OH, which is an alcohol functional group. And so methanol and isopropanol are members of the alcohol family because they have the alcohol functional group. So here are some of the functional groups. I am not going to test you on these. I want you to know that functional groups exist. Okay. So alcohols, ethers, aldehydes, ketones, carboxylic acids, esters, and amines. And here's the amine group is an NH2. So here you have a hydrocarbon portion, but then it's got this NH2 group. This affects the reactivity of this. This ethylamine is the smell of rotten fish. A lot of these organic chemicals have nasty smells. There's a few that have some good smells. Esters tend to smell nice, but not necessarily that one. Acetic acid. This is something we've learned about, right? Acetic acid. This looks different than how we talked about it in nomenclature, though, right? We described its formula as HC2H3O2. The acetate ion with a hydrogen on it. When dissolved in water, this is an acid. Look at this. Here we've got 3 hydrogens. There's the 3. We've got 2 oxygens, 2 carbons, and 1 hydrogen. So these are different ways of representing exactly the same molecule.
So the name doesn't describe how many hydrogens are in the
Acetic acid is a common name.
Sorry, I meant
For the hydrocarbons. The name, for hydrocarbons, the name does tell how many carbons are in that molecule. Oh, hydrogen. It does not tell how many hydrogens.
So it tells you how many carbons and the way it's arranged, and then you just fill in the hydrogen.
Yeah, we're going to stick to the straight chain hydrocarbons. So let's look at this one, no name. It almost sounds like no name, but it's no name. How many carbons does that have? 9. So to draw the structural formula, we're going to put 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. To put the correct number of hydrogens, we need to remember that each carbon will form how many bonds? 4. So the bonds that are not with the carbon atoms will be with hydrogen, because no name tells us 9 carbons. The rest of those bonds have to be fulfilled with hydrogen. This is a hydrocarbon. The only other element is hydrogen. So 4 is nice because you've got up, down, right, and left. So let me just put H's all over the place. And it gets a little tedious writing all the H's, which is why organic chemists have come up with numerous other ways to represent these things. future, I should probably change that to a shorter example, like butane or something. If we wanted to write the molecular formula for that, what would it be? C9H20. There's two ways you could figure out the 20. You could count them all, or you could look at this and say, okay, there's 9 carbons. They each have 2, top and bottom, and then we've got an extra one here and an extra one there. So it's however many carbons you have times 2, and then add 2. Now, I won't ask you a question like this, and hopefully it won't show up on the ACS exam either. To which family does this compound belong?
Ketone.
It's a ketone. And we have this carbon-oxygen double bond, not at the end. I think it's nice to expose you to these different kinds of compounds, but if you need to know this stuff, you'll have to take organic chemistry, and they'll teach it to you there. It gets complicated really fast. Well, any questions? Yay, end of chapter 3.